Okay, we stopped last week somewhere around this slide. We will go briefly through this part of the presentation because it is more or less self-explanatory. So we will maybe tell a few words about the development of multimedia systems or multimedia technologies. Until the advent of computers, presentations of certain media content were related to separate devices for playback of presentation. For example, we had this overhead projector to display the graphics or text. How it looked like, this was the overhead projector, and you put some kind of transparency above this lamp, and this lamp would collimate the picture through the lens on the wall. And it was completely passive, no electronics except for the lamp. And of course, the same thing was for the presentations. Presentations were really based on diapositive projector, slide projector. And that is the reason why we called a slide in PowerPoint presentation is one slide. Why in one slide? Because it was really a slide. So it was a film, positive film of very small dimension, 24 millimeters times 36 millimeters, and it was projected again with one lamp through these optics on the wall. And for that reason, it's called slide. For the audio part, we had magnetic tapes. This is a multi-channel tape recorder. We had turntables for records. For movies, we had camera projector like this one, or a bit more modern like this one. But nevertheless, for each type of media, you had separate recording device and separate playback device. Recording was much more complicated at that time. So you could record audio on this kind of magnetic tape. You could not record this kind of media because it was only done in the factory. So how to record the information on this disk, it was not possible to do it at home with some recording device. You only had to buy the audio record in the shop, and that was the only possibility. You had these big music companies that produce these records in large numbers, and of course they had some kind of studio equipment for recording of sound, and they later on for creating this template for the record. Historically, the very early version of records were of this kind. So the reproduction was completely mechanical, and the needle, when going along the groove on this plate, record plate, created vibration, and this vibration were transmitted through this horn, and you could hear the sound that was recorded only based on mechanical vibration. So the record was rotated, and as this needle went through the groove, it created this small vertical vibration that were amplified by this horn. Okay, so we had audio system for playing audio content. We had cinema video projectors for video content, and slide projector for displaying photos or slides for presentation. Nowadays, everything is centered around computers, either desktop computers or some handheld mobile devices, in a way that network computer is a universal integral system for playing of any kind of multimedia content. And today's computers are really close, or I would say even achieving this goal of being almost ideal, almost perfect multimedia, not only playback but also a reproduction system. You can use your mobile phone to record not only audio but also video. You can encode this video either in real time or maybe in some post-processing and then transmit it to the network or store it on your memory. And definitely, but as the technology is being improved, the expected standard of quality is constantly being raised. So the customers are always expecting higher resolution or higher frame rate or whatever. So there always will be some kind of demand to improve these multimedia systems, as well as to improve the throughput of the channel, of the communication channel that is used to transmit this data. And of course, the extremely large number of users that constantly use this system is extreme burden on these servers. They have to record I don't know many terabytes or petabytes, whatever, of video content each day. So they must have huge servers with huge disk space just in order to be capable to record all of these videos that are being generated by all of your mobile devices. And in that sense, there will surely be enough work for all of you if you go into this field. Okay? What are the challenges? The challenges is that we want to have multimedia content anywhere and anytime, and at any quality, I would say. But the mobile platforms, as they were being developed, they had different capabilities, different resolution, different memory, different operating systems. So it was a bit challenging at first how to make some kind of homogeneous standards, compatible standards that companies selling these devices supporting this standard would automatically ensure that this multimedia content can be either recorded or played back. Just as a touch from the history, it is the way that multimedia platforms looked only 20 years, let's say, ago. Nowadays, you have a multimedia platform in your pockets, and you just take your phone, or whatever, iPad, or some kind of playback device, and you can really have the highest quality video playback. It is fascinating how this technology has really advanced, and what is the current, I would say, state of the art of this. It is really astonishing. Especially taking into account that only 20 years ago it looked something like that. So it had some lousy resolution, some very small refresh rate, frame rate, maybe 10 frames or even less than that. And it was transmitted through channels that had a throughput of maybe 128 kilobits, or 0.1 megabits, what was really very small throughput compared to the nowadays networks, mobile networks. As I said, the challenges were related to differences in processing capabilities of your playback devices, platforms, differences in resolution, size, refresh rate, and quality of displays, power consumption limits. You know that if you use your phone for video playback, usually it will drain your battery maybe in 2 or 3 hours, and you have to recharge. Because definitely the decoding is much more demanding for processing power than when your phone is idle. But encoding is even more complicated. So if you run some kind of real-time encoding on your mobile phone, then definitely the battery will be drained maybe 3 times faster than only for the decoding task. Okay. There were also differences in the capacity of available memory for content storage, and the differences in the bandwidth of the communication channel that was used for transmission. Nowadays, with these modern mobile networks, these 4G, 5G, and so on, now it is really huge bandwidth, and there isn't any problem, I would say, that we have to compress that much video content as before. Before we had to compress this video to maybe some few megabits and that's it. But nowadays we can really stream to these networks several tens of megabits or even maybe hundreds of megabits throughput without any problem. And finally, there were also differences in the operating system. Now we have converged, I would say, only to 2 possible operating systems. So either it is iOS or Android. Most of the other are simply vanished today. So it is easier for the companies. They have to develop either for one operating system or for the other, and they will cover practically 99% of the market. Okay, I will go a bit further. So all of this is based or started from digital signal processing. And this digital signal processing is, I would say, cornerstone of these multimedia technologies. Why? Because I would say that a more accurate name of this digital signal processing was, or should be, time discrete signal processing, or processing over time samples of the signal. But due to the fact that in this time discretization, the signal values were converted to digital form, to numbers, for that reason, the name that was given to this field was then digital signal processing, because some kind of digits that represent the values of the signal were then processed by a computer. This name DSP derives from the fact that signal samples are represented by numbers, and necessary mathematical operations are then performed over these numbers to perform the desired function. Processing can be performed either by software or hardware solutions. Your mobile phone combines both. Some part of processing is done in hardware, some part of processing is done in software. Okay. And just a few words about this DSP. As a field, it is not that old. I would say that DSP theory matured somewhere around 60s and 70s of the last century. So we can say that this 50, 60 years old field of engineering. And it started, I would say, as soon as we had computer where we could perform this kind of processing. As soon the first computer arrived, then engineers had the idea, why don't we use the computers to do the signal processing instead of using analog circuitry. At the beginning, I would say this processing was performed exclusively by analog circuits, and digital signal processing was used only to simulate this analog circuitry, only to simulate the functional behavior, whether your analog circuitry is performing as you desire. With analog implementation, the maximum complexity of analog processing is directly determined by the complexity of the network that does this processing. And just as an illustration, for example, if you want to implement a sixth order analog filter, you would implement this filter with 3 operational amplifiers, cascaded in this fashion, where each section would implement second order transfer function. And with 3 such sections, we could have 6th order transfer function, and to tune the characteristics of this filter, you would simply select the proper values of these resistors and capacitors in the network. And you get the, I would say, guidelines how you should design this circuit, how to select the proper values of these resistors and capacitors to achieve the desired transfer function. In this example, this is a low-pass filter with a cutoff frequency of 1 kilohertz. 1 kilohertz. Initially, as I said, digital signal theory was used only to simulate the operation of such analog circuitry, just to verify whether we have computed the values of the resistors and capacitors properly, or maybe to see the effect of inaccuracies of values. So the tolerances of the resistors and capacitors, because each passive component has a given tolerance, maybe 1%, 0.5%, or as a cheapest version, 5% tolerance. And what you want to find out, what will happen with the transfer function if you allow these values to change by random value plus minus 5% of the nominal value. And through this simulation, you could easily find out, okay, the characteristics has changed, the cutoff frequency is not 1 kilohertz, maybe it is up or down. So it was used only for this purpose. And one of these famous programs that was used for simulation that is available still nowadays was called SPICE. SPICE simulation tool. And even nowadays they are used to simulate analog circuitry. And it is especially important if you design something for high frequency range, for some gigahertz range or several times. Then you need such tools to really quantify what happens with your analog components. Why is this important? Because all of these components, resistor, capacitor, they do not behave ideally. So these resistors, they have parasitic capacitance, parasitic inductance, as well as capacitors. They also have the parasitic resistance or some kind of inductance. And if you don't take this into account, then you would have some kind of not exact simulation. It works nice on the paper, it works nice maybe in simulation, but as soon as you implement it on your PCB, something is wrong, something is completely different. Because you have not implemented the real model of these passive components that has all of these parts, resistance, inductance, and capacitance, irrespective of the type of the component. And the same problem was with operational amplifiers, because their characteristics were not ideal as well. They had some cutoff frequency as well, so they were not behaving as ideal infinite amplification for all the frequency range, but simply they had first order pole going down from some maybe 10 hertz or whatever, and for this reason they had a lower gain with a higher frequency. And you had to model this as well. So in the simulation you simply said, I use the operational amplifier, this and this designation for that company, and immediately you took all of the parameters for this particular component into simulation, and this simulation was then exact. So they could really simulate what will happen if you use this particular operational amplifier. So it started all from this simulation aspect, but later on it was completely developed to really do the signal processing itself directly in the time sample domain. And people that maybe pioneered this field, the main researchers, the most famous, Alan Oppenheim, Ronald Schaffer, and Lawrence Rabiner, that introduced first textbooks, first lecture material for this topic. And the idea, the simple description of this idea, so you have the analog waveform, this solid line, and we have these dashed vertical lines represent position of samples, and we take only the values in these vertical lines to this AD converter. So we have these digits, we have a sequence x of n, instead of x of t continuous time signal, we have sequence of digits, sequence of numbers. And after this sequence is processed by a signal processor, by some kind of computer, and it will create an output sequence, y of n. And this output sequence is then fed to the DA converter, and from these vertical lines, which represent output samples, it will create this continuous line, solid line. It will do some kind of interpolation, and this will be the process signal y of t. So we start from continuous signal x of t, and finally end up with processed output signal y of t. So this is the basic architecture of any kind of digital signal processing chain. So we start from AD conversion, we have this processing part that processes this infinite sequence x of n and creates output sequence y of n, and finally, after conversion back to analog domain and after interpolation, we get the desired processed output. And what are the main advantages of this kind of digital signal processing instead of analog processing? First of all, the accuracy of operations can be adjusted to the desired amount by system design. So for example, if I need higher accuracy, I will simply use a larger word length or word width to represent the signal. I will use 8 bits or 16 bits or 32 bits to represent each particular value of the signal X of n or Y of n. So I can use this design as to ensure the desired accuracy. Also, the problem with analog component is that it ages with time. So the resistor value, for example, once you have took it from the factory and soldered it into your PCB, it has some value, for example, 10 kilo ohms. But after 1 year, after 5 years, it is not 10 kilo ohm anymore. It depends on the temperature range that this component was exposed, so it has some kind of maturing, and the resistor will change its resistance. How much? Maybe a few percent. It is given in some kind of simulation tables. They also have this specification. So what is the change of the resistance due to aging? You have to take this into account when designing such circuits, because otherwise you don't know what will happen after 10 years of operation. With digital components, we don't have this problem, because this value is stored as a coefficient somewhere in some table. And this coefficient is always the same. It doesn't age with time. So it is completely written in memory. It will always be the same today and whatever years from today. They also have the insensitivity to analog noise and crosstalk. What that means, when you have the analog circuit of this kind, then, for example, signal from this point should not feed back to the input. But if you have some kind of parasitic capacitance from this point to the input point, especially when the input impedance is high, then this parasitic problem is quite a challenge, because you have some kind of unwanted feedback, and it might cause even oscillations in your circuit. So instead of behaving like a filter, it starts behaving like an oscillator. So we get a tone at the output instead of having the desired operation of a filter. So the problem of undesired feedback is a very big problem when designing analog circuitry. The other problem is outside noise, because you might have some kind of additional sources around this device that create electromagnetic interference, and it is then coupled into the circuit, and again it creates some kind of unwanted signals in certain points in the structure. All of this does not happen in digital form, because we have these digital numbers and they do not affect one to the other. Simply we don't have this kind of crosstalk problem or noise problem. So that is a big advantage. Then it is possible to perform or to implement processing that do not have an equivalent circuit in analog domain at all. Some kind of digital processing, it doesn't have some kind of equivalent form in analog form. It cannot be done. It can only be done in digital form. And on the next slide, it is especially so for processing of signals in blocks. So, for example, if we want to compute the block transform of a certain sequence of numbers, input numbers, let's say that I took 256 samples from AD converter, and I want to perform fast Fourier transform or discrete cosine transform, I can do it on a computer, because I can store these samples into memory and then compute the discrete transform. But I cannot do it in analog form. So because it is completely infeasible. Then software-only based implementation is also very nice idea, because I can change this software easily. This software implementation is sufficient for many applications. For example, for audio processing and speech processing, I don't have to do hardware implementation. Most of the stuff can be performed as a program running on the general purpose CPU or on some specialized CPU dedicated for signal processing. Okay, and this software implementation, as I said, allows for easy adaptation of previously developed system to completely new tasks. So, for example, some new standard appears, and instead of producing completely new device and selling it to the market, you simply say, okay, the current customers can just change firmware in this device, and it will automatically support some new standard that was not available at the time the product was sold. Of course, it is not a very great idea for the one that wants to make money, because otherwise he will sell only one device and that's it, and the users will simply refresh this device with new software. They would much rather favor the version that they will sell a new device to you. Because, okay, now we have the new support for new standard, you have to buy a new device, throw this into the garbage, and buy a new one. So that is more or less a trend nowadays. As I said, very complex signal processing is possible in this time sample form. And this digital signal representation is also much more suitable for storage or transmission. Once I have this signal as a sequence of numbers, I can do any kind of storage, any kind of transmission much easily than with analog signal. And just to illustrate the basic idea how this signal processing looks like in this time discrete domain. So instead of having analog circuits, as I said, operational amplifiers, resistors, capacitors, and so on, we will have a structure whose block diagram is shown on this figure. The elements of this block diagram, this is the summator, addition of signals. It simply adds up value from this branch, and so on. This here is a multiplier. It multiplies the input signal by some constant, A of 0, A of 1. So I have some capital N filter coefficients that are stored in the memory, and I take this value, multiply with A of 0. Take this value with A of 1, and I simply add up all these values, and I get the output. And finally, what is this? Block Z to the power of -1. This is one step delay. So this is the operation that simply takes the sample from the previous step. So if the current step is x of n, then the output of this block was what was in the input in the previous time step. So x of n minus 1. If I add another z to the -1, I have to the step n minus 2, and so on. So I have a sequence of input signal. I have a sequence of input signal values, current signal value, signal from the previous time step, blah, 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 and signal from the capital N minus 1 steps before. I use this stored sequence of input signals to compute this dot product, as we say, because it is like a product of a row vector and a column vector. So I take the first value, for example, here, it is first entry from the row vector times the first entry of the column vector. Then another second element of the row vector times the second element of the column vector. So it is a dot product, row times column. And this structure has a name. It is called FIR structure, and the name comes from the fact that this is a filter of finite impulse response. Finite impulse response filter. So for that reason we call it FIR structure. And the difference equation that completely describes this operation is this summation shown with this equation. Y of n is simply weighted sum of x of n minus 0, n minus 1, n minus blah blah blah, up to n minus capital N minus 1. So it takes current input signal value and all preceding samples up to time step n minus capital N minus 1 and take weighted sum of these samples. And this A of k are weights that I use to compute this weighted sum, and these are constants. This A of k are stored in memory. These are filter coefficients. And their values are corresponding, let's say, somehow to the values of capacitance and resistors in analog circuit. So I have, again, new set of guidelines how to compute these values to have the desired transfer function of this digital filter. Okay. Another alternative to this FIR structure is the so-called infinite impulse response filter, IIR, infinite impulse response. And the basic difference is that instead of having one delay line only for input samples, I have two delay lines. One delay line is for input samples, and one delay line is for the output samples of the filter. And they behave completely analogously. So this here is a time input sample from the previous time step, from 2 steps before, and the same is here. This is the current output, output from the previous step, and output from the 2 steps before. And now I have this dot product on the right side for the Y branch, and I have this dot product for the input side, for the X side. And if I combine these together, I compute the new value on the output sample Y of n. So the pseudo-code to implement this filter would look something like this. So you have the current values of this state buffer. You have this value, you have this value. Also you have the current state values of this buffer. So you simply take this value times A of 1, take this value times A of 2, take this times B of 1, and this value times B of 2. Add this all together to the input signal multiplied by A of 0. And the output of this summation is directly Y of n. And after this, after we compute this Y of n, we have to update the state buffers. And update, what it means, this value is not needed anymore. So it is thrown into the trash. We don't need it anymore. This value is transferred to this state. And this value is transferred to this state as a preparation for next time step. The same here. So this value is transferred to this position, and this value is transferred to this position. And now the filter is ready to take a new value, x of n, from the input, and it can compute a new output value, y of n. And this is repeated in software. So to implement this operation, how many operations do you need? You have 5 multiplications with these coefficients A0, A1, A2, B1, B2, and 5 additions. You have to add this together to compute y of n. After that, you have this for move operation to do the state update, and you are ready to do the processing of the next step. So it is a rather simple structure, and this structure here is sufficient to implement one cascade of this filter implementation, second order system. Second order time discrete system that mimics this analog circuitry with one operational amplifier can be implemented as an infinite impulse response filter with this structure. So all you have to do, you have to compute these proper values of coefficients A and B, and you are ready to do the filtering of the input signal. Okay, so this is just a short description for the people that do not have the background in signal processing or signals and systems and everything else. Okay, then going further, so as they realized that this field is very important and that a really nice thing can be implemented digitally, they have also designed special processors that had a tailored architecture to be able to do this kind of processing more efficiently. So obviously, what kind of operations do you need? You need multiplications that should be fast. You need fast additions. Or maybe to combine both of them into a multiply and accumulate operation. Ideally, you would like to have instruction that can do one multiplication and accumulation in a single cycle. So that was the basic idea when introducing these DSP processors, to have instruction that is capable of performing one such multiplication. For example, this value here times A of 2, and addition to the current accumulated value in this summation. So addition and multiplication, they are all performed in a single cycle as a one instruction of this DSP processor. Okay? And they are called DSP processor. Why? Because it is abbreviation of digital signal processor. Not very clever, but okay, DSP. And as I said, so they have a dedicated execution units that are capable of performing consecutive multiplication and addition in very efficient way. And they support time parallel multiple operations within a single cycle. What also they can do, they can fetch another pair of arguments for the next multiply and accumulate operation. Because you have to fetch these arguments from memory into internal registers of processor. So you have to combine this fetch together with multiplication and addition of the previously fetched pair. So you have the currently, let's say, fetched pair. For example, this value here, it is in X register, and this value is in Y register. And this pair is used to perform multiplication with addition. But simultaneously, as you do this, you automatically fetch from the memory this value again to the same register X, and this value to the same register Y. And after this fetch, you also want to automatically update the address pointer to go to the next pair of values. So to the next entry from the X table, to the next entry from the Y table. So this automatical fetching, automatical update of the address pointers, together with this mark operation, all of this was done as a single instruction with multiple operations in one cycle. So that was the basic idea behind DSPs. An example of some early DSP from the company Texas Instruments, Texas Instruments 320, some C, blah, blah, blah. Nowadays, you would not buy a DSP as a separate dedicated component, integrated circuit, but it is usually integrated in the system-on-chip solution together with the main CPU, application CPU of your, for example, mobile phone. So when you have in mobile phone this ARM-based architecture, typically you have 4-core, 8 cores, or whatever. These are these main application processors with ARM architecture from this Cortex-A family. But together with this ARM CPUs, what you have on the same silicon is the set of usually 3 DSP processors. For example, the company that is very famous for this chipset and telephone market, mobile phone, is this Qualcomm, US-based company. So this Qualcomm company designs its own DSP processors. And this DSP is implemented together on the same silicon with this ARM, that is based on license of this ARM company. And together with memory, everything is placed on the same silicon. And this DSP does this time-intensive, mathematical intensive computation. So your ARM does not have to bother with this problem of signal processing. It does only the fancy thing, operating system, your application, blah, blah, blah. But some kind of real-time audio encoding, decoding, video encoding, decoding, it is performed on these DSPs. For example, this one from Qualcomm, it has a brand name Hexagon DSP, and usually it is a black box. So the programmer, it does not have ability to reprogram this DSP. It is like a completely closed firmware designed by Qualcomm just to implement the basic functionalities of your mobile phone. The most crucial ones related to the video, audio encoding. But lately, they have decided that out of these 3 cores, one would be available also for pre-programming. So you get some kind of programming interface, tools, and you are able to design part of your algorithm that runs on this DSP. And why is this important? Because this architecture is much more energy efficient than ARM. So in doing this kind of signal processing task, when you compute what is the watt-second energy implication of doing certain tasks, you will see that this architecture, it has much higher efficiency. It does the same task with lower energy consumption. And it is especially important for any kind of processing that must be continuously performed. When your phone is in sleep, let's say sleep is not in sleep, this DSP is constantly running in the background. And it is, for example, sensing any sensor of your mobile phone. When I walk in, for example, all of this phone is in sleep mode, it will sense each of my steps, counting my steps. And this is done by DSP. So this step monitoring, sensor monitoring is performed by DSP because it has much lower energy implication on your battery than running application CPU. Okay. And this architecture of a very simple DSP processor, just to have the basic idea, they have like parallel execution units, ALU units for arithmetic and logic operation, make unit that does this multiplication and accumulation operation, and they have a special dedicated shifter unit that is capable of performing, it's called barrel shifting. I can shift the value for any given number of positions left or right in a single cycle. So for example, I want to shift this value 17-bit position to the right. And on a normal CPU, you would have to perform 17 times shift to the left by one, by one, by one, by one. Here, you will have a single cycle operation, simply 17 positions in one cycle. So it is called like a barrel shifter. And they have dedicated address generation units that are working in parallel with execution units for the arithmetic. And these address generation units are capable of generating at least 2 effective addresses or 2 operands, one from one memory space, another from another memory space. And these pointers can be automatically updated by any given modifier after the access. By 1, by -1, by whatever step you want. And all of this is done in this dedicated hardware for address generator 1, dedicated hardware for address generator 2. And this architecture shown here is one very, very early DSP from company Analog Devices. It had designation ADSP 21XX. 21XX. Nowadays, you would not be able to buy this as a standalone circuit, standalone chip, because usually it is integrated as a core in some kind of total design. Okay, but just to illustrate, so this here is assembly code of this ADSP21 processor of company Analog Devices, and what is interesting, it does not have this usual assembly mnemonic form. You have the mnemonic of the assembly instruction and then the operands. It has this kind of algebraic syntax. For example, it says here this multiply result is equal to mx register 0 times my register 0, and both these values are treated as signed numbers, signed by signed. And then in parallel with this make operation, it performs one fetching from data memory from pointer I0 and one fetch from program memory from pointer I4. After the fetch, I0 is incremented by the value of modifier register M0, and after the fetch, this I4 is modified by M4, whatever it is in this modifier register initialized. By +1, by -1, whatever you want to go. So all of this is performed in a single cycle in parallel. And you have a dual loop, and this dual loop is also hardware controlled dual loop. It has dedicated hardware support to implement zero overhead dual loop. Yeah, not normally for classical computer, for classical architecture, you have a general purpose register, you initialize this register, decrement or increment, compare with some value. If not, jump back to the top of the loop. So, and you lose many cycles just to control the loop counter, conditional jump, and so on. Here, you don't have a single such instruction. You have this initialization of the do loop, and it simply performs all of these instructions to the last one with the labeled sections. How many times? This number of times. It has a dedicated hardware register that you initialize with how many big ones you have. And this part of here, these 6 instructions, 1, 2, 3, 4, 5, 6, 7, 8 instructions, these 8 instructions are sufficient to implement this structure here. So this second order structure, IRR, is implemented with 8 assembly instructions. And then if you have another such second order system, it is simply cascaded, it is simply involved several times, and you get whatever order you want divided by 2 by simply repeating this operation. We will make a break now because it's 3 minutes. So 15 minutes break. Do you have any questions? Okay, so I suppose that you understand everything. Okay, going further. What are disadvantages? We said what are the advantages of DSPs. But what are the disadvantages of such concept? Of course, one disadvantage is that we need A to D, analog to digital, as well as digital to analog converter for any kind of processing. And even the most dumbest processing, maybe we only want to amplify the signal, whatever, so we need a DSP. And that costs a lot, let's say, at least of energy, because we have to connect to the power supply, this DSP, and run the program, and everything else. The other problem is that the maximum frequency of the input signal is also limited. And you will see that it is limited by the sampling frequency of this AD and DA converter. This sampling frequency is bounded with the design of this AD converter. There are different designs of AD conversion and DA conversion, but all of those have a given bounds of the maximum possible sampling rate for this architecture of AD-DA conversion. And for some application, maybe audio and speech, it is very simple. So you have this high quality AD and DA converter that is a part of a sound card on your computer, or even integrated on a motherboard as a one chip that is this codec chip that does this A to D and D to A conversion. And you have this analog input and output on the normal 3.5mm jack on your motherboard. The same thing is with your mobile phone. It uses the same kind of AD and DA converter, and these are suited for the audio range. And that means that the sampling frequency is sufficient to quantize and to sample with no loss of quality audio signal, high fidelity audio signal. It means the sampling frequency is either 44.1 kilo sample per second, 44 kilohertz and 100 hertz, or another standard is 48 kilo sample sampling rate. And nowadays they have even higher sampling rates, like 96 kilo samples, or even twice that, 192 kilo samples for the audio rate. Okay, and if you have only, let's say, 44 kilo sample per second, then the time separation between two neighboring samples is quite large. It is, let's say, 5 microseconds that you have 5 or not 5, how many? Not 5, 25 microseconds between two neighboring samples. And these 25 microseconds, you can easily perform processing of this kind. For example, if your CPU runs on only 10 MIPS, so you could do 250 assembly instructions between two samples. And you have here maybe 8 instructions times whatever number of different sections, and much less than these 250 instructions. You can do this in real time. But as soon as the signal frequency is higher, it is not only maybe 20 kilohertz as audio signal, but something even higher than that, whatever, video, for example, then this sampling rate is insufficient, of 44.1 or 48 kilosample. You must use faster AD conversion rate. And nowadays, you have dedicated AD converters that are really going into gigasample range, that are capable of sampling input signals with a sampling rate of order of several gigasamples per second. And this type of converters are usually integrated into what is nowadays called this software-defined radio. Maybe most interesting example of this kind of software-defined radio is this USB stick for digital TV broadcast, DVB-T. So you plug in this USB stick into your laptop and connect the aerial antenna to the input, BNC, and then you have a receiver capable of receiving this high-frequency radio signal, and this reception and later on processing is done digitally. So practically AD conversion is done immediately after antenna, preamplifier, or maybe after the first mixer. So you have the first mixer that transposes this spectrum band to some baseband, and this baseband is then sampled with this high sampling rate AD conversion. After that, instead of having analog signal, you have sequence of numbers. And this sequence of numbers is processed, but in this case in hardware, not in software, because the rate is too high to do any kind of software processing. But all of these operations that are depicted here can be easily performed in hardware as well. You must have hardware headers, hardware multipliers, corresponding structures, registers to store these state values. And the architecture of such system is then called software-defined radio, although it is not really a software. It is configuration that defines operation of this hardware. Hardware is configurable. So you have set of these multipliers, adders in these kind of structures. You can define the coefficients of these filters in a set of registers, initialize them with software, and after that, this hardware implements this operation. And this stick costs only around 20 or 30 euros or dollars, whatever. And it can be configured to receive a huge range of frequencies, from maybe several tens of megahertz up to several gigahertz. So a huge range is covered with a simple chip that is programmable. You simply set the center frequency of the band that you are interested, the bandwidth select, type of modulation, blah, 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 and immediately you get from this USB output this I and Q signal, in-phase and quadrature signal, that can be used later on to demodulate this signal and to decode the message coming from the radio transmission. And just as an example, with simple Raspberry Pi computer and such USB stick or with this RPL SDR receiver, you can have either, for example, this ADSB receiver for the transmission from the aircraft. So all aircrafts, modern aircrafts, they have this active transponder. They emit in some kind of in part of the spectrum a message. So identifying the plane, number, whatever, then position, geographical position based on GPS, heading, everything is simply transmitted to the Earth receiver, and then visualized in this software like Flight Radar 34, blah, blah, blah. All these receivers are sending their information to the server, to this cloud, I would say, and based on this collected data from many receivers around the continents, they get all these messages coming from all planes running around. The similar thing is, for example, with meteorological, these balloons that we have for meteorological sensing. They also have this transponder that while flying up and down, the balloon explodes at around 30 kilometers height above the Earth. But during this flight, it continuously monitors the temperature, humidity, and pressure computed from the vertical position from the GPS location. So this message is transmitted to the receiver, and this message can be recorded or captured with this simple RTL SDR receiver that costs only 20 or 30 euro, and whatever computer you use, for example, Raspberry Pi, that does this decoding. So it is called software-defined radio because it is configurable. So this hardware is configurable in a way that you can easily set coefficients for this processing for any desired kind of modulation, demodulation, everything else. Okay? Going further, now we will go to this part that describes quantization and discretization, time discretization and amplitude quantization, as well as the issue of reconstruction. So almost all modern multimedia systems, they have this conversion of this input physical value at the very input of the system. So they convert this physical quantity into electrical signal, and electrical signal is fed to the AD converter, and we get a sequence of numbers. So this multimedia signal is then represented as a sequence of numbers through the process that we call sampling as a temporal or spatial discretization. Temporal in time, if it is time signal, or spatial if it is two-dimensional signal, like an image. Then we have to sample this image on the regular grid, and we get the pixels. So it is then spatial discretization. But not only this, we have this quantization, because this output value is a digital number of finite precision. So instead of having infinite precision of analog value, we have finite precision. For example, let's measure it with multimeter, whatever, you have only given number of digits to measure the voltage or the resistance, whatever. The same is with AD converter. It has a given number of quantization levels that is given by the design of this AD conversion, defined by the design. First of all, we will cover this aspect of signal sampling regarding time discretization. This time discretization is actually conversion between continuous signal, x of t, into series of samples. So far, we will assume that these samples are not quantized in the amplitude, but only time discrete values of the signal. And these signals, these samples are equidistant in time. So I will have a sampling period, and this sampling period, capital T, will be the same for all the samples. So what it does, it actually takes this value of continuous time signal x of t at regular time intervals, integer number n times sampling period capital T. And we then have this regular time sampling, and a reciprocal value of this capital T is sampling frequency. So this capital T is sampling period, and 1 over capital T is sampling frequency. Okay, and sampling is performed, this time discretization is performed either inside of AD converter itself, or sometimes in front of it by a dedicated circuit that is called sample and hold device that does this sampling, and it will take the sample, keep this continuous value until the AD converter converts this value to digital form. And then take another sample, again keep this analog value for a given time until the conversion is done. This sampling and hold device can be integrated into the AD converter, or it can be implemented as a separate component in front of it. Okay, and now we come to the basic question of ambiguity or unambiguity of time discrete representation. The question is, if we have analog signal x of t and its corresponding samples x of n computed in this way. The question is, what is the mapping between these two signals, between continuous signal and X of n. Is it a unique mapping? Because only the active mapping has the index, let's say. I somehow would like to be able to go back to X of t from X of n. Not only going from X of t to X of n, but back from X of n to X of t. So this invertibility or question of ambiguity is very important. Because if we have two different signals X of t that produce the same sequence X of n, we have a problem. We don't know which of those was that generated this sequence X of n. So it must be unique sequence X of n representing unique signal X of t. Only then we have this bijective mapping between these two domains, continuous domain and time discrete domain. And then, of course, if it is bijective, but is it possible to reconstruct X of t from its corresponding samples without error? I would like to have perfect reconstruction. Once I have this sequence of numbers, I ask myself, is it possible to go back to X of t without any loss of information, to get the same signal I started from? And the answers to those questions is actually this Nyquist-Shannon sampling theorem. And this sampling theorem is named by inventors, two guys. One was Harry Nyquist, and another one was Claude Shannon. So they both came to this theorem independently. For that reason, it is called Nyquist-Shannon theorem of sampling. And it says, very simple, according to this sampling theorem, a necessary and sufficient condition to fulfill this ambiguity is that input signal should be band limited to the highest frequency that is 1/2 of the sampling rate. So, for example, if the sampling rate is 10 kilo sample per second, then signal must be band limited to half of that, 5 kilohertz. If you don't have any energy above 5 kilohertz, this signal can be uniquely represented by its samples, sample with this 10 kilo sample per second. And if you take these two values as a quotient, it turns out that this 2 samples per period sufficient to achieve reconstruction. So you only have to sample at least 2 samples within 1 period of the signal. If you have 2 or more, it is reconstructible. If you have less than 2, you cannot reconstruct. Okay? So it says here at least 2 samples per sine signal are sufficient to reconstruct this initial signal perfectly. This figure nicely illustrates this aspect of sampling. So we have 2 signals, blue and red one, and samples are here. First sample, second, third, fourth, fifth, sixth. As you see, both signals have exactly the same sequence of samples. But obviously they are not the same. So which of those is the proper signal, properly sampled, and which is improperly sampled? Or out of this, which one would be sampled according to Nyquist-Shannon theorem, red or blue? How many samples per period does red have? 1 sample, 2 samples, 3 samples, 4 samples, and this is again from the next period. So it has 4 samples per period, definitely more than 2. So I would say this red signal is properly sampled. It has 2 times higher number of samples per period than the given limit by the Shannon-Nyquist theorem. And the blue one, if I compute how many samples it has per period, this is 1 period, 2 periods, 3 periods. In 3 periods, I have 4 samples. 1, 2, 3, 4. And this one is from the next bunch of 3 periods. So 4 samples per 3 periods. So 3 times over 4, it is less than 2. So it is not sampled sufficiently high of high frequency. Sampling rate is insufficient. So obviously, this blue signal is not properly sampled. So the signal represented by these signals, by these samples, is the red one. Because if the blue one is at the input, I could not distinguish later on from red or blue. This sequence would give either blue, but the proper one is the red one. because the red one is satisfying the Shannon-Nyquist condition. The blue one is too high frequency. So its frequency is much higher than it is allowed by this Shannon-Nyquist theorem. It is higher than half of the sampling rate. Higher than half of the sampling rate. And obviously, one element that is needed to ensure that no such signal like blue signal occurs at the input of the AD converter is a special filter, analog filter, that is called anti-aliasing filter. It is low-pass filter. Its only function is to really cut off the band at half of the sampling rate. So after this highest frequency of half of the sampling rate, the energy of the signal must be zero. So nothing must pass above half of the sampling rate. Only part of the spectrum from 0 to half of the sampling rate, that is half, should be passed by this anti-aliasing filter. This filter can also be integrated as a part of AD converter or implemented as a dedicated circuitry in front of the AD converter. Okay? The sampling is a problem not only for one-dimensional signals like a waveform, speech, audio, whatever, but also for two-dimensional signals. If you have insufficient or insufficient spatial resolution, we have the same problem of aliasing. And how it looks like, for example, we have this brick wall that was properly sampled. It means that the image was represented with a resolution of 615 times 750 pixels. So now I can see the edges of all bricks and the mortar between them. I can see the nice picture, a regular brick wall. But for example, if I have the resolution that is decimated in spatial resolution 3 times, so 3 times less pixels per x and y dimension, what I get is some kind of waves here. You see these waves. And these waves are so-called Moire pattern. And this Moire pattern is actually artifact of aliasing in two-dimensional signals in images. Because this is actually a low frequency signal coming out as a result of insufficient sampling rate. You have slow variation in intensity, something that is bright, dark, bright, dark. Okay, this slow spatial frequency, low spatial frequency, is a consequence of insufficient sampling dimension, let's say, it's the spatial dimension. So this pixel size was too large.
So if it were brighter, the frequency would be higher. So that's what you're saying.
No, it is the separation between these fringes, black and
Between the pixels.
yeah. So the fact is that the frequency, the changes in the image itself are too fast for this kind of sampling rate. And it happens, for example, when you have a suit that has a regular pattern, and you stand it onto the camera on a certain appropriate distance from this camera, this separation between stripes becomes comparable with the pixel size. And in this case, it might happen that it only captures black stripes. Or with the phase shift of 90 degrees, it only captures white stripes. And what you get the flashes, black, white, black, white. So instead of having a nice suit with stripes, now you look like a seal going from flashing dark to dark, white. So it's very important that going to the TV and giving interview or whatever, you should have a homogeneous suit, some kind of nice color, not some kind of stripes. Regular pattern, because this regular pattern interferes with the discretization of the pixel density, pixel separation, let's say, pixel size. And this is then called Moire pattern, but it is the same problem with continuous signal, one-dimensional. If we sample, for example, just an illustration. So if I have sinusoidal signal, and if I sample only at these points, what I get a DC value, constant value. So I get the sampling rate that is equal to the signal frequency. And for example, I take always the value of the maximum where the sign passes +1. But with the phase shift, maybe I will take only these values, 0. So I will get again these values, but of 0 value. Or maybe with another time shift of 180 degrees, I would get -A values. So I would get a constant amplitude of -A. And that is this, if you have stripes in image, then it is either completely white or completely dark.
Depends on the frequency.
Depends on the frequency. The separation, so if this distance between two lines is exactly equal to the 1 pixel volume, then you get the problem. Okay? So it is an issue of proper sampling for the images. Okay. And now we go to the issue of reconstruction. So we want to reconstruct the signal, the original signal. And the theory shows that reconstruction is possible. And at least theoretically, mathematically, reconstruction is possible. And if I start from original signal, x of t, and if I simulate the operation of time discretization by multiplying this signal with a periodic pulse train of Dirac delta functions. For example, this here, this here. I have a periodic sequence of Dirac delta functions separated with period t. So this period is equal to the sampling period. And what I get discrete signal plus delta, minus delta, plus delta, minus delta. Maybe I'm missing something. I'm not in phase. Okay. This one is minus, this one is plus, this one is minus, this one is plus, and so on. So I get again periodic train, but each of these delta function is modulated by the value of the signal at that particular time instance. And this is this signal xs of t, xs of t. So this signal is xs of t, while this was x of t, this blue one. Now what I'm interested in is how does the spectrum of these two signals look like? So what happens in the spectral domain with x of t and with xs of t? So what is the difference? The original spectrum, blue one, was this some kind of band-limited spectrum in the bandwidth plus minus b. But the spectrum of this black signal, xs of t, it has periodic extension of this original spectrum that is repeated to the left and to the right infinitely times. So due to this discretization, what I get the periodicity of the spectrum with a period that is equal to the sampling rate. So minus half sampling rate to plus half sampling rate, and that is a fundamental period of the spectrum, which is then repeated infinite times left and right due to this discretization in time. So in spectral domain, the effect of discretization in time is periodic extension of the spectrum in the spectral domain. So it becomes periodic. And now, if I want to get back to x of t, the only thing I have to do is I have to get rid of all of these replicas. I have to filter out all of the neighboring replicas, infinitely many number of them, and only keep the central replica of the spectrum from minus fs half to fs half. So I have to filter out everything except this part of the spectrum, because this part of the spectrum is identically equal to the original spectrum of the continuous waveform x of t. And this filtering out is performed by filter that has this kind of rectangular magnitude response, ideal rectangular magnitude response. And due to the fact that it has these vertical edges, we call this filter brick wall filter, like a ball of bricks going vertically down. if I compute the impulse response, so the inverse Fourier transform of these characteristics of this rectangular filter transfer function, I get corresponding time domain impulse response that is so-called sinc function. So this sinc function is actually the impulse response of the filter that should be used for ideal reconstruction. So if I pass this signal, xs of t, this train of Dirac pulses modulated by signal, if I pass it through the filter that has this kind of impulse response, I will get the original signal ideally. What it means? You know that if I take the integral, the original function has this form, okay? So what I have to do, I have to do the superposition of these sinc functions with the corresponding value of each sample. So this is the contribution of this sample here. So I place this sinc function at the position of this sample. Then I place another sinc function on the next sample, for example, this one. So this is a negative sinc function going like that, we will know, hopefully. This sinc function has a period that passes exactly through 0 on all neighboring samples and passes through 1 on the position of the sample that I'm interpolating function, that I'm computing contribution of this sample. According to this expression, I shift this sinc function left or right to the position of the nth sample. So this n is the index of the sample. So t minus n times period. So it is just a shift left or right by n times the period. Normalization over t because it is normalized sinc. And this sinc function is defined as sine of pi times t over pi times t. Very simple function. So a sine function of pi t over pi t. Of course, you should answer yourself what happens at t equal to 0, because you have sine of 0, it is 0. You have in the denominator again 0. You have 0 over 0. You can only compute it by limits. The limit of this quotient when t goes to 0 is 1. Because when the sine has small argument, the value of sine is equal to the argument. So for small t, it is only pt over pt. And this cancels out, it is 1. So for that reason, I have this value of 1 at t equal to 0. But at each neighboring sample, so when this t is equal to 1 or to minus 1, it is sine of pi or sine of minus pi. It is 0. Or 2 pi, again, 0. So I have zeros at all neighboring samples except for this one that I am computing the contribution of. And what I have to do, I have to add up how many such functions, whatever number of samples I have. So if I have infinite number of samples, I have to have the contribution of each particular sample as an infinite function. One function, another function, another function. And if I add these infinite functions together, I will get the original signal x of t without any loss. It will be exactly equal to the original signal if the original signal was unlimited. So if I didn't have any frequency component above half of the sampling rate, the reconstruction would be ideal. So what is the problem with this kind of filter? Does anybody know why this filter is not really implementable or applicable? What is the main problem with this filter? Is it causal? The first question. Filter is causal only if the impulse response is different from 0 after t equal to 0. It means it cannot make prediction of the input. So it has the response only after the input. So realizable filters that can be implemented, they have the impulse response only after this point. It's a non-zero impulse response. To the left, it must be 0. So otherwise, this part of the impulse response asks for samples that are still to come. They are not available at this time. They will be available in 10 samples, 100 samples, whatever. So this part of the impulse response is non-causal part of the impulse response. And it can be implemented only by the delaying the construction. If you have all the samples available in front, if you store them in memory, okay, you have all the samples, and now you can go back or forward, whatever, in time, in any desired direction, whatever. But if you have AD converter, you cannot predict what happens in 10 samples or 100 samples, because contribution of these samples that are still to come is defined here, with this tail, with this negative tail. So the actual implementation is always truncated to a given length or whatever to the left side. And that is paid by addition to the delay. You introduce delay into actual reconstruction, whatever number of samples, for example 10 samples, and create output signal with this design delay, I would say. So the only way that I can take the contribution of these 10 further samples is to acquire them and to compute the output only after this delay of 10 samples. And in this case, I can implement this part of the impulse response 10 samples to the left. If I need more, higher accuracy, I have to increase the delay. 100 samples, okay, then I have the delay of reconstruction 100 samples, but then I have higher accuracy of representation because more of this negative part is implemented in the construction. So it is a trade-off between the accuracy of reconstruction and delay. If you want to have higher accuracy, you must introduce higher delay into DA conversion. Okay? And nowadays, this kind of interpolation is performed as a part of so-called oversampling AD and DA converters, or sigma delta, so-called sigma delta AD and DA converters. They have architecture that is based on this kind of almost ideal sync interpolation, and this interpolation is done in an oversampled time discrete domain, because this digital filtering is easier to be done than analog filtering. So most of this filtering required to do this brick-fold filtering of the spectrum is done digitally, and only the last part is done analogly, with some RC circuit. So they have only a passive filter with one capacitor and one resistor to do the final analog filtering. But most of the filtering is done in the oversampled digital domain, where this oversampling factor is maybe 128 times or 256 times to achieve almost ideal operation as the sync filter described here. Okay? And it is integral part of your audio codec that is integrated either in your phone or on your sound card in your computer, or this codec that is on the motherboard. So all of these audio range AD converters are based on this oversampled sigma delta architecture. Okay. Going further, now we will go to the next part, and this next part, maybe we'll make a break. Now it is 3 minutes to 6. So we have a break, and then after the break we'll start with a new chapter. Questions maybe regarding this? This oversampled AD conversion became popular when the first CD player was introduced. So when you had this first CD player based on this compact disc and a laser that reads the disc, and corresponding DA converter, it had this oversampled DA structure. And it was called mesh, multi-shape, multi-something, noise shaping. Multi-something, noise shaping, mesh architecture. You can easily find the description of this architecture of DA conversion as well as AD conversion on many websites, on Wikipedia, everything else. But the drawback of this is that if you want to introduce oversampling by a factor of 128 or 256, you cannot go too high with the sample rate, because otherwise this circuitry must operate internally at the rate that is 2 order of magnitudes higher than the final sampling rate on the digital sequence. And it is a limiting factor. So this internal hardware of this AD converter must function, must operate at 250 times higher frequency than the final sampling rate at the output of this AD converter. And it is okay for the audio range, where you have the 44.1 or 48 kilohertz. It is few megahertz, few mega samples. You can design such circuit. But it is a big problem if you want to design this kind of architecture for some radio signals, where the final output sampling rate is some gigahertz, let's say. Then you cannot use this kind of structure. So the AD conversion that is used in this RTL SDR USB 6 is they are flash converter architecture. Flash converter means that it compares the input value simultaneously to all levels of the AD converter. So for example, if you want to have 7 output bit codes, linear codes, with values from minus 64 to plus 64. So you will immediately compare the input value with these 128 levels and find out which of these comparators is a breaking point between less than or higher than, and simply encode this information as a 7-bit value. And in this case, it can achieve this huge rate of gigasample per second because it doesn't have any processing, some kind of operations like multiplication, additions. It doesn't have a successive operation of comparison like this successive AD conversion. It is like when you are on the market and when you buy whatever oranges, and then they have this analog weight, and then they put 1 kilo weight on the left side, orange, it's not enough, half kilo, oh, then not enough, 1/4 of a kilo. It is a principle where this successive approximation, AD conversion, it runs on that principle. So it's half of the scale is compared first, and then it is either higher than the half of the scale or lower than the half of the scale. Then you take another smaller weight, 1/4 of the scale. Okay, is it still higher or lower? And you successfully go to the lowest possible, whatever, 1/256 for the 8-bit conversion, and you get the final balance between the weights and your oranges. So of course they need at least 8 successive steps to do the comparison if they want to have 8 bits of the output. But it takes 8 clock periods to get the result. First weight, another weight, blah blah. While this flash AD converter, it does it in 1 step. So it simply simultaneously compares input value to all 128 or 256 levels and simply finds, okay, which of those converters was below and which are above the threshold. Okay, the code is this. And with this architecture, they can really have the sampling rates of gigasample per second. I will show you, I will open during the break one data sheet of such converter. And you can see the specification of such chip. Okay, now they have break. I have opened here one example of modern AD converter from the company Analog Devices. It is maybe most famous for this AD conversion. For example, they produce one AD converter, AD9680, and if you go to this product brief, it says it is a 14-bit, 1.25 gigasample per second converter. It can operate also with 820 gigasample, 500 megasample rates, and very, I would say, important is this amplitude resolution quality, these 14 bits. If you really need high precision, you must quantize the signal with the highest possible resolution, and it costs a lot. So, for example, this AD converter that is part of this RTL SDR receiver that costs 20 or 30 whatever euros max, is only 8-bit resolution. So it has a gigasample range, but it is only 8-bit resolution. But for example, if you want to have 14 bits of resolution for each sample, then it costs much more. For example, if I try to find the pricing for this component from one of these electronic distributors, Mauser, you can see the price is 1,143 euros for one piece, and if you buy 10, you will be discounted, so it is 1,139 per unit, per piece if you buy 10. So it's quite a lot. And the reason for this high price is very complex design. To be able to have this 14-bit resolution, you have to simultaneously compare input value to 16 to 2 to the power of 14, 16,000 different levels.
Yeah, but is it worth it, like the
huge
amount of money differential just have more bits?
Yeah, so this is very important. There are different tricks how you can have this, they call it processing gain. Processing gain, how to apply different clever DSP algorithms that can cancel out this noise, quantization noise. They can reduce this quantization noise and still get the useful signal, but only if the band is narrow. So these tricks, this processing gain, is really a gain, but only if you operate on narrow spectrum bands. But if you, for example, want to transmit very wide band signal, then it is very important to have high resolution, because you cannot achieve the same thing. Yeah, so you have to pay with the money. And this is usually part of these radio base stations, because they don't have a separate receiver for each channel. They have a receiver that is wide receiver for n channels simultaneously. And then they do the processing of each channel digitally. So they sample the whole band simultaneously as a wideband signal, and then do the processing in digital domain, separating channels, blah, blah, blah. And to do this, they must have this kind of high resolution, high sample rate converter. Okay, and that costs a lot. But if you have a narrow band, you can go with 8-bit, and it is sufficient to have a reception of a signal, demodulation, with small error rate, and so on. Okay? The similar architecture is also used as a part of CCD, so for scanning of your camera picture, let's say. So they have this CCD sensor, which is essentially a set of capacitors that they have charge proportional to the number of photons that fell on each particular sensor. And you have to measure this very small charge, some picocoulombs, whatever, by selecting column, selecting row, and sending this value to the AD converter. And this AD converter must be capable to convert the whole image, the whole megapixel resolution, 120 times per second, or 60 times per second. And to do this, you have the very high required sampling rate. And it can only be done with this architecture of flash AD converter, and it is integrated as a part of CCD sensor. So they have this active part of the sensor matrix, but each column has one AD converter that converts these corresponding rows into the digital value. Okay. Okay, now we'll go to the next chapter. The next chapter is related to the quantization of the signal value, not only discretization of in time. Okay, exactly as we introduced. So what if we have to know the value precisely? So not only roughly maybe in 256 levels, but maybe more accurate, 1024 or whatever. 2 to the power of 16. In multimedia system, quantization is typically performed after sampling immediately as a part of AD conversion, but also this quantization is part of lossy signal compression. So I would have a signal of nominal resolution at the output of AD converter, but later on I will try to somehow compress this signal to extract only the important part of the signal that should be encoded, transmitted, and reconstructed, and all of this redundancy should be removed somehow, identified and removed. And this reduction, compression, can be done also as an additional quantization step performed on the nominally sampled and nominally discretized signal. So you have, for example, AD converted it is 8-bit, but later on we decide, okay, we will now quantize this to only 4 bits because you have to save the bandwidth and so on. So the sampling is integral part of the AD conversion, but it also can be introduced as a 2G compression to reduce the required bit rate. Okay, so the signal that is at the output of AD conversion that has a nominal quality, nominal quantization, usually we will call this signal raw signal. It has nominal accuracy. This signal can be further transformed by means of coding procedures into encoded signal, and the type of this encoding can be either lossless or lossy. So lossless means that exactly the same message should be reconstructed on the receiving side without any loss. Exactly the same bit message. But if I'm allowed to introduce some kind of losses, then maybe I can achieve even higher compression ratios than for lossless coding. And practically all nowadays video coders are lossy coders. But you don't see this quality degradation because they are cleverly designed in a way that this loss is invisible, not perceivable. It looks almost ideal to the original signal, although it is maybe 20 times of lower rate than the original signal coming out from the AD converter, from the sensor. Okay. And if I want to mathematically describe the quantization operation, the easiest way of modeling quantization is simple round operation, mathematical rounding to the nearest integer. So I take the real value x, I divide this real value with the step size, I get again the real number, but now I convert this real number to the nearest integer. And I get this value x cubed, or not x cubed, maybe not yet x cubed, but integer number representing the sample. And after I multiply this again by the step size, I get the quantized value. For example, just to be figurative, let's say that the step size is one quarter, and our value was 0.3. And if I divide this 0.3 with the step size, 0.25, it is something about 1. And after rounding this value to the nearest integer, I would get, okay, this is 1, integer 1. And then if I again multiply this 1 with a step size of 0.25, I will get x quantized, that is 1 times 0.25. And that is, of course, 0.25. And I have the difference between the actual reconstructed value and the original value at the input. And I have this error, and the error is 0.05 in this example here. And I know that this rounding would create the error that is always in the range of plus minus 1/2 of the quantization step. Because if I'm slightly below the half above the level, then I'm maximum error positive. Slightly below, I have to plot it. So with this rounding, so this is this midpoint value. This is plus 1/4, 1/2 of this delta. This is minus 1/2 of the delta. So 1/2 of the delta. Minus 1/2 of the delta. So the whole range is quantized to the same value I, corresponding to the central value. And the error is at most plus 1/2 step size, or at least minus 1/2 step size, due to this rounding to the nearest integer. Okay, so it is, for example, 1.49 is quantized to 1, or 0.51 is quantized again to 1. So the whole range from about 1/2 to 1.5 is quantized to the value of 1. Okay, and this operation is then modeled as a simple mathematical expression. Simply divide the input value x with the step size, take the nearest integer, and then multiply back with the step size, I get the quantized value. Okay? Just as a few notes about the signal quantization. This kind of quantization described by this equation is commonly known with the abbreviation PCM, coming from pulse code modulation. Why pulse code modulation? Because the idea is, for example, if I have a 4-bit code, so I have 16 levels, so the codes are from 000 to 111. Okay? And then I send these 4 bits sequentially for the first sample. This is first sample, another sample is, for example, 10, another sample is 1100, blah, blah, blah. So the idea is that the value is represented by the code. And that is the origin of the abbreviation pulse code modulation. The value of the signal is a packet of, in this case, 4 bits, because I have only 16 levels, and I have this sequence of 4 bits, blah, 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 regular sequence, and this code is then represents the value of the signal. Alternatives to this pulse code modulation were different schemes known as pulse amplitude modulation. The idea was that the amplitude of the pulse corresponded to the value of the signal. So higher pulse represented higher amplitude value. Or another way is pulse width modulation, where the width of the pulse represented the value. So wider the width, higher the value. The period was constant, but the duty cycle was changed. So the percentage of how long the signal was in the high state in comparison to how long it was in the low state. So I have this ratio that was from 0 to 100%, and that was representative of the value of the signal behind this one period. Another way was pulse position modulation. So I had the reference pulse, and the position of the pulse was varied based on the signal value. So it was called pulse position modulation. And the final two are this sigma delta and adaptive delta modulation. They have quite in common with this structure that's used in oversampled AD conversion. The reason that it's called sigma delta AD converter is precisely that they have this kind of sigma delta structure in front of this oversampled digital implementation. And this part is analog. This sigma delta modulator is analog circuitry. And only after that you have the digital part that operates on oversampled rate, but it starts with only 1 bit precision. So the trade-off is between the oversampling ratio and the resolution. So the basic idea behind oversampled AD conversion is the trade-off between sampling rate and quality, amplitude, resolution. So at the output of this sigma delta modulator, you will have the sequence of only 1 bit, 1 0, 1 0. And this sequence of 1 bit, 0 1 is digitally processed with digital filter to create a 16-bit value represented by this sequence, highly frequently changing 1 0 1 blah blah blah. If you have alternatively changing 1 and 0, it means midpoint value 0. So if you have 50% in time in 1 state or 0 state, it is exactly midpoint, and it represents this 0 value. If it is completely in 1, it is maximum positive, completely in 0, maximum negative. So we have this high frequency binary sequence generated at the output of this Sigma delta modulator, and this high frequency binary sequence is the input to the digital filter that computes the 16-bit value encoded by this high frequency binary sequence created by this Sigma delta modulator. Okay. This is just for terminology to know other alternative ways how engineers were also proposing how to do the modulation, how to represent analog signal with some kind of pulses. And this most famous that's been used nowadays is this PCM, and it comes from sending one bit after other and representing binary value with a given resolution, 4-bit, 8-bit, 16-bit, whatever. Okay, so AD converter is characterized by two basic parameters. As we said, first of all is this step size, so how big is the step, and another is how many quantization levels you have in altogether. So, for example, if I have 8-bit converter, it means I have 2 to the power of 8 levels, 256 levels, and if it is bipolar AD converter, it is 128 negative, 128 positive. Okay, and if I multiply this number of levels with the step size, I get the dynamic range. So what is the difference between the lowest input voltage, highest input voltage? So what is the total dynamic range of the AD converter? The input signal must be adjusted with its amplitude and bias to correspond to this dynamic range of the AD converter. So if they say it is plus minus 1 volt around 0, then the input signal conditioning must be such that whatever the signal is, it must be converted to this range, because this is a linear part of the range that this AD converter can convert to close. If you have, if your signal exceeds this limit, so if it goes above the highest possible positive voltage or below the lowest negative voltage, then you have this saturation or over-excitation. This value cannot be represented. It is represented with the highest possible positive code or with the lowest possible negative code. But you don't know the actual value, because the actual value is saturated with a given dynamic range of the converter. So you have to take care that the dynamic range is adjusted properly, that you don't go, that you not exceed this range that is given by the AD converter. For actual AD converters, you also have the problem of the reference voltage, because the absolute accuracy of measurement is based on the absolute accuracy of the reference voltage that you supply to one pin of this AD converter, because it only gives the ratio to this reference voltage. So, for example, if the value is whatever maximum value, it is integer ratio to this value that you have supplied to one input pin. And if you want to have given absolute accuracy, you must have very high stability of this reference voltage that is insensitive to the temperature, to the changes in the power supply voltage, so it must be stable. And sometimes it means that this voltage reference is also thermally stabilized in some kind of closed loop. It has some heater that constantly keeps the thermal reference on the same temperature. For example, 40 degrees Celsius, whatever the output temperature is. So it has some kind of regulation, closed loop regulation, that ensures that this reference chip, silicon chip, is kept on the same temperature. So in this case, the value is guaranteed to be within 1 per mil around the nominal value and so on. Okay? As we said, to facilitate implementation, usually the number of levels is a power of 2. So, for example, 8-bit, 16-bit, 24-bit. because it is then easier to implement this digital circuitry if it is power of 2. And for that reason, we usually express the resolution as a number of bits, how many bits we have. So this exponent of 2 is the number of bits. Okay. Of course, if we know that resolution is B bits, and if the dynamic range is capital A, then the step size is this total dynamic range divided with the number of levels. So A times 2 to the power of minus B, so divided by 2 to the B, is the dimension of one step. And this one step defines what we call granular error of AD conversion. So this is this granularity. What is the smallest step size? What is the smallest increment that I have to make in order to have another code at the output of AD converter? If the change of input value is smaller than this smallest possible step size, then of course code is the same. Code does not change at the output. I cannot sense this kind of small change of the input value. And for that reason, if I want to have high accuracy, I must have high resolution of the AD conversion. In this case, the step size is small. Okay, and finally, usually AD converters are bipolar, and that means that this total range is divided with 2 equal halves, plus minus a half, to be able to represent positive and negative voltages. Typically, the input range is plus minus 1 volt for these converters. So I have to condition this input signal, whatever its value is, that it must be either amplified or attenuated, such that it is exactly around 0 plus minus 1 volt. And in this case, it is within the dynamic range of the AD converter. Okay, so typically, if you have this bipolar converter, then the output code is encoded with this two's complement representation. So the positive values are then from 0 to, for the example of 4-bit two's complement, I would have only 3 positive values, 3, 2, 1, 0, and 4 negative, minus 1, minus 2, minus 3, minus 4. So this is non-negative part, let's say, because 0 is whatever, non-negative. And we have this negative part, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, and 1, 0, 0. So in this two's complement representation, this is the negative part of the representation of the input signal, and above is the positive part. And if I want to find the value of the signal, so this value is what? 3 times over 4 times a half. This value here is 1 times over 4 times a half. Because the range is from plus a half to minus a half, minus a half. Total range is A. But as you see, I don't have the value of plus a half. I have 1 step size smaller value, because this two's complement representation, it lacks the highest positive, let's say, value. I don't have 4, I have only 3 as the highest positive value. Of course, I have minus 4 on the negative side. So I have the exact value of minus 4 above 4 times a half, what is exactly this value, but I don't have this value. This value would be code, again, 4, but this code does not exist in a two's complement representation. Okay? Resolution directly limits the accuracy of AD conversion. As I said, because all input voltages that deviate at most plus minus 1/2 step size are represented in the same code, same output code. So this is this granular error. And for that reason, the quantization operation is not reversible. Once I do the quantization, I cannot go back to the actual real value. I don't know what was the actual value. It is the whole range is represented as a single integer number. Okay? So I cannot dequantize the input signal, the digital signal. Okay, and now we come to the mathematical part of this discussion, and what we want to do is to somehow measure or validate or say what is the quality, objective measure of quality. So what is the objective measure of quality or degradation that is introduced by quantization? And to measure this error, what we would do, we would use some statistics, let's say. We will do some statistics, and we will treat this signal as a random signal. But not only signal, but the quantization error will also be treated as a random signal. And once we apply the theory of random signals and systems, we can easily find the variances of these random signals, the expected quadratic value of these random signals. Why? Because these variances are measures of the energy, let's say. What is the energy of error compared to the energy of the signal? And once we have these two energies, we can take the ratio. So what is the ratio of the signal error energy to the signal energy? This quotient is then computed, taken logarithm of this quotient. So logarithm of this quotient defines signal to noise ratio expressed in decibels. So this representation, this logarithmic representation is very important to us because our human perception of quality is more or less guided by this logarithmic scale. So not linear scale, but logarithmic scale. So what is our perception whether something is twice as good or twice worse? It is more or less corresponding to the logarithmic law. And for that reason, instead of using the linear measure, we are converting this quotient of these two energy into logarithmic measure by simply taking the logarithm of this quotient, and what we get are the decibels. And these decibels are very compliant with our, I would say, perception of the quality. Okay? So it says here, samples of the signals can be viewed as a realization of a random process X. So I have a random process X with some kind of distribution, and I have also another random process that is for the error, for the quantization error. So this sequence can also be treated as a random process. And in our derivation, we will assume that these two random processes are independent of each other. What is completely wrong. But nevertheless, it simplifies the theoretical discussion. We will later on show that this assumption is valid under certain circumstances. This assumption that these two sequences, these two random signals are independent of each other. But it is wrong when the resolution is very small. When the number of bits are very small, then this assumption becomes rather poor. And you have this correlation or whatever, dependence between the error and the signal, and the theoretical derivations are not accurate enough. Because the real world is behaving differently than this theoretical assumption that these two are independent random variables. Okay? So we start from this here. Okay. So it says here, variance of signal is the expectation of something. What? A random variable subtracted by the expectation of this random variable. So what this says here, for example, I have the population of students in our classroom. And I ask myself, what is the expected height of an average student, let's say. I put you in a row from the smallest to the largest, and I say, well, okay, what is the expected height? How can I find this? What I have to know is the probability density function. So I simply have to count how many times I have measured height of 150 centimeters. How many times 151, blah, 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 up to the tallest guy, 2 meters, whatever. Okay, so I have this frequency distribution. like a histogram. And this histogram is approximation of the continuous probability density function for each possible real value of the human height. Not only for integer values in centimeter, but also for all possible values in micrometers, let's say. So this PDF is like a limit case of the histogram when this bin size reduces to 0. When you have infinitely narrow bin sizes, then you get the continuous probability density function. And that is the most important part that we start from, this PDF, probability density function, that will model the statistics of the signal, but not only the signal, but also the error. The error signal, E, X, also, both will be modeled by corresponding probability density function. Okay? And once we have this probability density function, once we have this PDF, so if I have this histogram of student height, it should not be 0, something. Okay? So this histogram, in the limit sense, it represents some kind of continuous function, continuous density function that is underlying density function, because if I have a classroom of only 30 students, then this is only one realization of this statistical process. I have only 30 samples. So I'm missing maybe height of 175 centimeters. Nobody is of that height, because this is only one realization. But the underlying statistical distribution is a continuous function, the red one. So I start from this red one. This, I would denote it with fx of x. And this function is a density function, which means that if I integrate this function for all x's, what I get is 1. I have 100% probability that student is of any weight or height. So total integral of probability density function must be unity. Okay. Now, when I know this function, this continuous function fx of x, if I want to find the expected height of our students, the only thing I have to do, so expectation of this random variable of this x, is integral of x times fx of x dx over x's. So instead of integrating density in the whole range, I integrate product of x times density. If I do this, I get the so-called first moment. And this first moment is the expectation of the random variable. You know that if you would want to find this expected value for the given number of students, 30, you would use the average value. And this average value is what? It is only one estimate of the expected value. One estimator. I use the sample average as an estimator of the expected value of the height of pupils in classroom. And this estimator is a best unbiased estimator for what kind of distribution of the input signal. What should be the input, the distribution fx of x? For the case when this simple sample average is an unbiased estimator of the expectation. If the input distribution is Gaussian, normally distributed process. So if the input distribution is Gaussian, then this simple sample average, by adding this height and dividing by the number of students, is an unbiased estimator of the expected value, but not for other distributions, because you might have bias if the input distribution is not Gaussian or symmetric, I would say, in a simplistic case. But then, the same way as I have this sample average value, so sample mean, as an estimator of the expected value of the random variable, the same way I have this sample variance. So I compute the standard deviation. So by simply subtracting this mean value from each sample, taking the squared value and dividing by n minus 1, I get the standard deviation, taking the put value, I get the standard deviation of this bunch of students. So how much is the standard deviation around this average value? And this standard deviation is the unbiased estimate of the sigma. So variance, square root of variance. Again, only for Gaussian distribution. So if the input distribution is Gaussian, then this sample standard deviation is an unbiased estimator of the variance. And for that reason, if our process is Gaussian, we can use simple sample mean to estimate the expected value, and we can use sample standard deviation to estimate square root of variance. Okay? So if I want to compute the actual variance, sigma x squared, what I have to do, I have to find the expectation of what? Expectation of random signal x with removed bias, with removed expected value, and then taken squared. This is what I have to do. So I have to take the random variable, I have to remove the expected value of the random variable, square this difference, and find again the expectation of this quadratic error. Okay? How can I do this? Exactly the same way as I did for the expected value. The only thing I have to do is I have to find the integral of this here, x minus x, expectation of x squared, times fx of x dx over x's. And I will get sigma x squared. Okay? Because this here is a function of random variable. The random variable is x. And if you want to find the expectation of a function, the only thing you have to do, you have to multiply this function with the PDF of the random variable and integrate it along all the values of these random variables. So this is the way that this variance is computed analytically. And if I want to do it, if I want to approximate this with sample mean and sample standard deviation, then instead of using the expectation, I will use this sample mean. So I have only n samples from fx of x, and I have this sample mean x dash, that is simply sum of xi, I1 to n over n, average value, and this is approximation to the expected value of x. And once I have this, I take standard deviation, that is sum of xi minus this x mean squared over all I, and then divide it with n minus 1. This is STD squared. It is proportional, it is approximation to the variance. And that is this, what is written here. So this variance is this expected value of this random function. Okay? So if the input process is Gaussian, then these two estimates are unbiased estimates. So sample mean is the unbiased estimate of the expectation, and simple standard deviation squared is the unbiased estimator of the variance. Okay? But what we will do in our experiments, we will use these theoretical expressions to find these integrals, but also simulate the whole thing with actual numbers. And then we can use only sums. Since we have finite number of samples, then we must use simple mean value, standard deviation, everything else, as the estimator of the underlying statistical expectation or statistical variance. Okay? And that will be basics of our analysis that will be presented next week. So, just to conclude, we have only 3 minutes more. This probability density function fx of x depends on the input signal. The error probability density function depends on the parameters of the quantizer, but also on the signal from which it originates. But nevertheless, we will assume that they are independent. That somehow the quantization error is practically independent of the actual signal. Why? Because we can say, okay, this error is always plus minus 1/2 of the step size. And if the signal is, I would say, lively enough, if it goes through all the levels of the AD converter, more or less if it behaves randomly, then more or less this error would be of equal probability in the range of minus plus half, minus half of the step size. So it will have uniform distribution of the error, and this uniform distribution of the error of the bit that is one step size plus minus 1/2 is independent of the signal itself. But it is not true if I have a synchronous sampling. If I have a, I would say, unfortunate case that I sample the signal always at the same value, then the error would always be the same. So it will not be plus minus randomly 1/2. It will always be the same, maybe 0.3 step size. So it will be like a Dirac in the probability density function instead of having uniform, simple uniform probability density function for the random, completely random error. So this assumption is valid only when the input signal is lively enough, going to all levels, going to all errors, such that statistically it covers the whole range plus minus 1/2 of the step size equally, with equal probability. In this case, it is much simpler to derive the final representative of the error, this signal to noise ratio. Because if I have this uniform distribution of the error, then I can easily compute the variance of this error directly from this step size. So this will be the topic of the next lecture. So we'll start from this basics of the statistics of the probability density function, and then we'll go on to apply this theory to the description of the quantization process. Okay, maybe those that are not familiar with this field of probability densities should consult maybe a few pages of the textbooks to remind themselves about this. Okay, see you then.